My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I'll be discussing disk scheduling. I'll be introducing the purpose of disk scheduling, talking about some classical and historical disk scheduling algorithms, talking about native command queuing and disk schedulers that are currently in use in the Linux kernel, and then I'll talk a little bit about how I/O requests can be efficiently scheduled on solid-state drives. Now, scheduling serves two purposes. Disk scheduling serves two purposes. The first of these is to arbitrate disk access among different programs. This ensures that competing programs have access to disk resources, and that a single program cannot monopolize the disk resources in such a way as to prevent other programs from accessing the disk. With mechanical hard drives, scheduling algorithms historically have also attempted to improve disk performance by reducing the number of seeks required, reducing the number of times the drive head needs to be moved. If the drive head has to be moved too many times, a lot of throughput can be lost from the disk because we're waiting on all those seek times to occur. The simplest scheduling algorithm would be the first come, first serve algorithm, which is implemented in Linux as the no-op scheduler. This algorithm is extremely straightforward. It simply consists of a FIFO queue into which new requests are added. The requests are removed from the queue in order, one by one, and these requests are sent to the disk for processing. Now, there's no reordering of the queue. This is a first come, first serve ordering. So back-to-back requests for different parts of the disk may cause the drive head to move back and forth across the platters, wasting quite a bit of time with seeks. Historically, several attempts have been made to try to improve this behavior. One example would be the scan algorithm, or the elevator algorithm. And in this algorithm, the drive head only moves in one direction. It serves all the requests in that direction before moving back in the other direction. This is called the elevator algorithm because it's modeled after how an elevator works in a building. The elevator leaves the ground floor, moves to the highest floor, stopping along the way to add passengers traveling up, remove passengers at whichever floor they wish to stop on, and then once the elevator reaches the highest floor, it turns around and comes back down. Same process here. In this example with the scan algorithm, assuming that the head starts at sector 1, and this request for sector 50 comes in while sector 61 is being processed, the algorithm is going to process the requests in order 3, 12, 32, 40, 42, 61, 84, 97. And since that request for sector 50 came in while 61 was being processed, that request for sector 50 is going to have to wait until the head changes direction and returns to sector 50. Now, there are a few optimizations of the simple scan algorithm. The original algorithm proposed that the head would move all the way from the beginning of the disk to the end of the disk, and then all the way back to the beginning. The look algorithm improves upon this behavior by moving the head only as far as the highest numbered request before changing directions and moving it back down. The circular versions of the algorithm, cscan and clook, only serve requests moving in one direction. So for example, with circular scan, the head would start at the first sector, move all the way to the end of the disk, servicing requests, and then come all the way back down to the first sector without servicing any requests and start the process over again. These are historical algorithms in the sense that with modern drives we have LBA or logical block addressing, and so we don't actually know where the disk is placing data physically. This type of algorithm was used historically with cylinder head sector addressing, where we knew the physical properties of the disk, and the idea here was to reduce average seek time. At no time did we know where the platter was. That was up to the disk to figure out. so there was no way to reduce rotational delay, only minimize seek time. Another algorithm that attempts to minimize seek time is the shortest seek time first algorithm, or SSTF. This algorithm actually orders requests by sector location. So when the request for sector 50 comes in, it's kept in an ordered queue, a priority queue, and the next request to be served by the disk, these requests are still sent out one at a time, is chosen by looking at whatever request is closest to the current disk position. Historically, this could result in starvation, because if a bunch of requests come in for one piece of the disk, requests for the remainder of the disk might not be processed for lengthy periods of time. Furthermore, once again with logical block addressing, the operating system doesn't really know where the sectors are laid out on disk, and so this algorithm doesn't really work with modern hard drives. Also, with solid-state drives, this algorithm assumes there's a disk head, which in the case of a non-mechanical drive, there is not. In the Linux kernel, an approximation to shortest seek time first was implemented with the anticipatory scheduler. This was the default scheduler from 2.6.0 through 2.6.17. It was removed in 2.6.33 because it's obsolete. The idea behind the anticipatory scheduler was to approximate shortest seek time first by ordering only the read requests into an ordered queue, into a priority queue. If the next read request was close to the current head position, that request would be dispatched immediately. Otherwise, the scheduler would actually wait a few milliseconds to see if another request arrives for a nearby location. And starvation was avoided in this algorithm by placing expiration times on each request and adding preemption, so that if a request was waiting too long, it would go ahead and be serviced regardless of its location. The idea here was to reduce overall seeking. There was a separate queue for write requests because write requests could be performed asynchronously. We did not have to wait on those requests to be completed before a process could continue doing useful work. This algorithm was shown with low performance drives to improve performance on web server applications. However, it was shown to have poor performance for database loads, where there were a lot of random reads and writes on the disk, and with high performance disks, this algorithm actually breaks down. Modern hard disks generally do qualify as high performance disks. The reason being is that they implement something called native command queuing. This is a feature of newer SATA drives, and basically native command queuing leaves scheduling of disk requests up to the disk itself. The disk circuitry and firmware makes the decision about which request to handle next. To do this, the disk has a built-in priority queue of about 32 entries, and the disk is able to schedule its requests automatically, taking into account both the seek time and the rotational delay, since the disk knows the location of the platter. This makes modern disks much more efficient, and this works with logical block addressing. The operating system's role with this type of hard disk is really more arbitration of the disk resources among the different programs running on the system. One modern Linux scheduler that can be used for such arbitration is called the deadline scheduler. And in this scheduler, the kernel maintains separate request queues for both read requests and write requests, similar to the anticipatory scheduler. Reads are prioritized over writes because processes typically block or stop and wait while waiting to read something from the disk. Thus, writes can be done later at some point when it's convenient for the operating system. The waiting time in each queue with the deadline scheduler is used to determine which request will be scheduled next. A 500 millisecond request time is the goal for read request. This is the time it would take to start the request, with a 5-second goal to start a write request. This scheduler may improve system responsiveness during periods of heavy disk I/O at the expense of data throughput, since each request has a deadline and the longer a request has been waiting, the sooner it will be scheduled. This is especially useful for database workloads because there are many requests for different parts of the disk. However, for web servers and other services that try to access large quantities of data located in the same location on the disk, this particular scheduler can actually reduce total throughput. Completely fair queuing is a somewhat different idea, where instead of actually scheduling the I/O requests, the completely fair queuing model schedules processes or running programs to have time slice access to each disk. And essentially, this CFQ scheduler gives each process an I/O time slice, and that process can do as much I/O on the disk as it would like within that time slice. When the time slice expires, the CFQ scheduler moves on to the next process and gives it access time to the disk. There is a little bit of similarity here to anticipatory scheduling, since a process can send another request during its time slice and try to get that request in without having a lot of seek time. However, this algorithm can waste time if a process does not immediately turn around and send another request. Thus, it can reduce the overall disk throughput, since there could be idle times while waiting to see if another request will come in before a time slice expires. This has been the default scheduler in Linux since 2.6.18. Now, for solid-state disks, we have to choose a scheduler that accounts for the fact that there's no seek time to worry about on the disk. The anticipatory scheduler, the elevator algorithms, shortest seek time first, all of these algorithms can actually reduce performance on a solid-state drive because they make assumptions about minimizing head seek time, and we have no heads to move with a solid-state disk. Completely fair queuing can also reduce disk performance because of idling at the end of a time slice. That's true for any disk. So what do we do to maximize performance for a solid-state drive? There are really two good choices for a solid-state drive. There is the no-op or FIFO scheduler. This works well for general-purpose systems. However, when there are heavy I/O workloads and we want to maintain system responsiveness, the deadline algorithm is useful, since other processes will have more opportunities to access the disk. In summary, operating systems are arbitrating disk access among different processes to prevent one process from monopolizing the disk and preventing other processes from having access. On older disks with cylinder head sector addressing, the operating system was also attempting to reduce seek time, thus improving aggregate disk performance. However, newer SATA disks with native command queuing schedule themselves to reduce both seek time and rotational delay. Thus, algorithms that attempt to minimize seek time are unnecessary. Furthermore, with solid-state drives, scheduling mechanisms that are based on old mechanical assumptions can actually reduce performance. So for SSDs, we're really only interested in arbitration.